So welcome back to another episode of Controls. Last we left off, we looked at the forces and moments block here. Now we're going to go in more of the towards the AV block, as well as the accept commands and compute environments. Here in the property space block, we're computing the linear equations, non-linear equations of motion. So we're going from body accelerations, inertial velocities, attitude rates, and positions, and we are computing those equations. I'll show you here. So this is not from me; these are from the slides taken. So yeah, this is how we move from the inertial to the body reference frame. Solve for acceleration this way: u dot, v dot, and w dot, and then these are the three cases for your plane. So straight and level flight, steady level turn, and symmetrical pull-up. The value of the acceleration to be different based on your flight condition. So you can see here for this first case, unaccelerated means that your linear and angular accelerations are 0, and your angular rates, PQR, are also 0. And also means the sum of the forces and moments also equals 0. Okay, so back to the simulation. Okay, so let's go on to the scopes block. So it's a lot easier to analyze data if you can format it in terms of graphs. So that's what we've done here. So we have it together in longitudinal, vertical, and lateral directional, as well as you have your linear. This is based on a command of 10 degrees alpha from your trim angle of attack, and as well as a command, a roll angle of 5 degrees. So this is kind of showing the different things you could look at. You can like pitch rate, pitch attitude, elevator position, throttle position, your airspeed, and of course you can look at the lateral directional of that. So that's going to be a phi, psi, heading angle, aileron command, as well as rudder command. And then in terms of the rates, you look here at PQR. So remember, so these are your angular rates, Q dot, P dot, R dot, and then let's see here, let's go to U, V, W dot. So if you want your plane to be in trim, you want to be at trim at basically t equals 0. So you see at the start for each of these. So at the start, U, V, and W dot, they're all 0 here, and they all converge to 0 no matter what flight condition you are in. The script section of the simulation. This is obviously in MATLAB, and let's start with the what we call init. So sim init. This is basically if you're familiar with programming rules, like this is the script that you run before starting simulation. So it kind of initializes all the variables. So if you go by one, so this is initializing the engine and environmental constants, as well as determining which flight condition you want to run the script. Trim settings I'll get into. Here we initialize the initial conditions, as well as determine the dimensional and non-dimensional derivatives, as well as estimate modes, stabilize the matrix, and here we have our gains, different gains based on roll, pitch, yaw, and altitude, hold. So that's some in it. So let's break it down. So if we go into flight conditions, we have the 3 flight conditions for the B747. We have approach, cruise, as well as landing, I believe. Oh no, this is high-speed cruise. Okay. We have approach flight condition, cruise, and high-speed cruise. So obviously you could implement different flight conditions for other airplanes. In the Roscom book, they do have other configurations that has this kind of data, but just real quickly go over it. You have the airframe properties, the flight condition data. So that's going to be current airspeed, altitude. Q bar is your dynamic pressure. C bar is your mean aerodynamic chord. Then you have mass data, so it's your weights, as well as your moment of inertia. And then these coefficients are basically have have been non-dimensionalized based on the properties of the plane. So you have coefficient of lift, drag, pitching moment, zero lift drag coefficient, partial pitching moment with respect to whatever whatever perturbation your plane is doing, as well as your lateral directional control and moment and hinge moment derivatives. So that's the flight conditions block, script. And then dimensional derivatives here, this is calculating your let's see, axial force, thermal force, pitching moment, side force. So basically this is calculating all the forces that's acting on your plane in flight. And then, so the difference between these dimensional derivatives and the stabilizer matrix is um, this is based on perturbations on your plane. So if you kind of look through the Roscom book, it will kind of go through how exactly to compute these. I will not go over in this video. That could be something I could do, but for now, I'm just kind of giving you an overview of exactly what these are. These transfer functions are basically how we um, come up with those league lag compensators or PID controllers based on the root locus plots. If I run this real quickly, it should output. Okay, let me 1 second. So this is the output of all the root locus plots. This is based on change in elevator or aileron or rudder inputs. So this is kind of how you evaluate the performance of the plane based on the location of the poles and zeros, and how we determine what kind of compensator we do need to what's based on your requirements, and you want to design to those requirements based on the root locus plots. Or another way would be using Bodie plots, gang phase. That's something I could touch upon, but let's just give an overview for now. And then your estimate mode script. This is estimating your full gauge, short period, industrial modes based on your damping ratio and your natural frequency. Let's see, constants block. So environmental constants, this is computing your sea level properties. That's going to be your sea level density, viscosity, temperature. Um, and then thrust constants, this is just going to be based on the configuration of your plane, number of engines, thrust per engine, as well as the position of each plane relative to the FRP or fuselage reference plane. And yeah, I think that's it. So all of those scripts should be run in the siminit script right here. So um, that is how we operate the simulation, everything from the siminit script. And yeah, that's a good overview of the simulation. And you may notice there's another SLX file here. This is your lower order equivalent system model that we kind of use to estimate the inner loop control laws. I will touch upon this in the next episode, but for now, I just give a quick overview of what this is. So this is working in a linear system and kind of evaluates the performance of the plane based on these inputs and again pitch, roll, yaw, and throttle, and we're using these control laws to control the performance of the plane. So let's see if this, hopefully this runs. Oh, then I can keep, but so what we do is we start with this. Okay, it's not running out. We start with this linear order system, and then once we're happy with it, we can implement this whole thing right here. These control laws are taken and basically cut out and pasted into our AVA block over here. So if I go up this level, so all of those control laws are directly pasted in here into our nonlinear system. This is what that is. So